friction is intrinsically electromagnetic. It is believed that friction is due to the result of the intramolecular interactions between the two surfaces. As everything is all made up of atoms and atoms contain protons, neutrons, and electrons, then the protons on one substance will be attracted to the electrons of the other object. And that bond is what creates friction. And it's an interesting way of thinking about it because if the two objects have a chance to hang out together, the bonding is very strong. Meanwhile, if you let them glide, even though friction still exists, they don't have a strong bond with each other. A great way of showing this is that whenever you're trying to move like a couch or a refrigerator, what do? Exactly, you give it a big heave. You're trying to break those strong intellectual bonds, and after that, even though friction still exists, you're able to push it more comfortably. This points out another important fact, and it's that the force of static friction will be greater than the force of kinetic friction. All right. So static friction are when the strong bonds are formed, and kinetic friction is when the weak bonds are formed because they're moving relative to each other. And scientists have found out that it does work out to a fairly strong correlation that friction is a constant. It's a constant that's proportionate to the normal force. So the greater the normal force, the greater the corresponding force of friction. If that's true, then all we need is the letter K constant to associate the two together. In other words, FF is equal to some K Fn. But they don't want to use the letter K. I don't know why. Maybe because the letter K is overused. Instead, they use the letter mu mu. This one over here. Elongated U. Maybe you've seen it before. All right. And this formula can be written two ways. The force of friction for static friction or the force of friction for kinetic friction. All right. Use the one as appropriate. The values for your mu will be different. Remember that when the two objects are stationary to each other, the stickiness is a lot stronger. And once they're in motion, the stickiness between the two is a lot weaker. So you should expect the value of mu to drop between mu s and uk. And take a look at that on the lookup table. It is true. Do you need to copy this chart down? No, you don't. It's in blue, after all. But you should just be able to read it. All right. So if I give this to you as a reference for any quiz, test, or exam, you should be able to interpret it and recognize which values you should be using. All right. Interestingly, between metals, they do form a very strong static bond with each other. That's exactly what they use in the relationship between the train's wheels and its tracks, right? Metal versus metal. Always a very strong correlation of friction, coefficient of friction between the two. All right. And yes, once it's in motion, then the coefficient of friction decreases quite significantly, which is why it's always important for you to drive on dry concrete. You can imagine how the values drop under wet concrete. It goes from this to that. Worse off, if you end up locking your brakes, look at how much the values decrease by. As much as 4 times, all right? So you have 4 times less grip between the car and the ground when the ground is wet. I shouldn't be using the term grip because grip has to do with deformation. In other words, the ability for one object to deform itself into the cavities of the second object. That's why tires have all those openings for 2 reasons. One of them is for the grip so that you can have better traction, but it also gives you space so that there's place for water to travel. Because if the water can wick away at the small little openings, then you don't have that slippery surface between the two, switching you over into this dangerous realm. Okay, of wet concrete. We want to keep the contact between the rubber and the ground as good as possible. Okay, so this does become a common issue of, well, what happens if you go out of control? Have you guys ever tried Tokyo drifting with your bike as a kid? You know, when you pedal forwards and then you back pedal and the back bike's wheels lock up and then your back wheels just start tilting. Wasn't that so much fun? Well, what you're really doing is that you're switching between the static universe and kinetic universe. I know this sounds rather weird, but while a wheel... I wish I had a wheel around. Improvise. While a wheel is rolling on the ground, what kind of friction is it between the wheel and the ground? Static or kinetic? And many of you guys will accidentally say that is kinetic friction because you see the wheel rolling. but you should really be paying attention between the relationship of the wheel itself and the ground. And you can see that between the surface of the plastic and the ground, it's not rolling on top of each other. It's just making brief contact and breaking that contact. So that is static friction. If you want kinetic friction, that's this. Okay, so kinetic friction, static friction. Okay, so yes, while a wheel is rolling on the ground, it is static friction until you lock up your brakes. Again, it's a big issue when the ground is wet, and that's why most vehicles have something called ABS, or anti-lock braking system. What you're seeing in this diagram over here, no, those are not gears. Instead, it's spokes of metal, so that there's a little metal detector nearby it. So as the spokes are moving around, it either detects metal or it detects a void, detects metal, detects a void, metal, void, metal. It's a quick way for it to tell whether the wheel's spinning or not. And for a car to brake properly, the computer expects all four wheels to decelerate at the same rate. In other words, the rate that it sees metal and doesn't see metal is constant. However, if one of the wheels do lock up in the wintertime, then the velocity or the rate of turning of the wheel suddenly goes down to 0. The computer recognizes it, then suddenly it's going to let go of the brakes for a brief moment to get the wheel up to speed again. Because anytime the wheel locks up, you're experiencing this Tokyo drift, you're going into kinetic friction, the car loses ability to steer properly, and that's rather dangerous. All right, so that's why ABS, it constantly turns on and off. You'll feel in wintertime. It's constantly braking and unbraking each of the wheels separately to ensure that they're all decelerating at the same rate. Now you know. Oh, last thing to point out. The coefficient of friction between Teflon, static, and kinetic. You might think that they're the same value, but you got to keep in mind that these are approximations, okay? It's approximations. In other words, we really don't know the coefficient of friction to a high degree of certainty or precision. We only approximate it. You'll notice that for the most part, coefficient of friction is either 2 or 3 sig fig, and that's about it. All right, don't expect to have any coefficients of frictions greater than 3 sig fig. You're not going to see anything 4 sig fig because it is an approximation at the end of the day. Okay. Things to keep in mind. The surface area does not matter. I know this sounds rather weird. All right. So imagine this box over here. Okay. It doesn't matter if I glide on a surface like this, or like this. You may argue that there's less surface over here, but at the same time too, this weight over here is being pressed over a smaller surface area. In other words, there's a greater pressure between the two. On the other hand, when you lay it like this, you're dividing out the weight over a larger surface area. So really the surface areas and the pressures cancel each other out, and that's why the coefficient of friction remains exactly the same. So it doesn't matter the surface area itself. Okay, we're assuming that that this guy over here is not digging into my hand, right? Because if it did, then that would be traction. Okay, we're not dealing with traction. We're really dealing with two smooth surfaces rubbing against each other. Okay. Again, when the surfaces are moving relative to each other, then it's kinetic friction. So let me just go through that one more time. All right. In this case over here, this is kinetic friction. What about this? It's still kinetic friction because they're moving relative to each other. Well, what about this? This is known as static friction because they're not moving relative to each other. Okay. And as I mentioned, once you break those strong intermolecular bonds with each other, then you switch over from the static realm into the kinetic realm. It's easier to push an object while it's in motion. Armed with that knowledge, let's go through some examples. Okay. In fact, we're going to revisit a previous example. You may recall this one from the beginning. Okay. Let's say you decide to accelerate an object with a force of 5 newtons. Well, 5 newtons divided by 2 kilogram mass gives you 2.5 meters per second squared. We'll use that as a reference number. Okay, 2.5. Well, what if we turn on friction? Okay, now with the frictional values, you need to look it up on a lookup table. In general, wax is a really good lubricator, so that's why there's a fairly low coefficient of friction here at 0.12. In fact, with coefficient of friction, you can often treat it as if it was a percentage. That's how I think about it. 12% of the normal force, right? After all, when you look at the formula, FF is equal to mu K Fn. So mu K is equal to FF divided by Fn. So in other words, it's a Newton force divided by another Newton force. Newton divided by Newton becomes unitless. So mu k is unitless, but it is a ratio, and that's why 0.12 is the same thing as 12%. Okay, so just keep that in mind. Mu s and mu k are unitless. Okay, so let's start solving this problem. Now, this free body diagram isn't complete yet. What is it missing? Good, the force of friction, right? And here's the thing, you have to think about it intuitively, all right? There's no mathematical formula that can predict for you which way the force of friction will be. You got to look at the situation over here. And obviously, if there's only a force acting on it towards the right that's causing it to accelerate, the force of friction must oppose it and move towards or push towards the left. All right, so now we have our fighting pairs. Can we solve for this dimension? No, not yet. As we know, force of friction can be only determined if we know the coefficient of friction times the corresponding normal force. So that's why in these problems over here, you always solve for the y dimension first. Okay, so even though ff is equal to mu k times fn, we got to solve for fn first. So we got to deal with the y dimension. F net y is equal to the normal force, subtract the force of gravity. We know this object's not going to fly off into the air. It's not going to sink into the ground. So F net y goes to 0. In other words, in this case over here, Fn is equal to Fg, and Fg is equal to mg. So we multiply the 2 kilograms by 9.81 newtons per kilogram, and that will give us 19.62 newtons. You start to memorize these things after you practice it enough. Now, as for the coefficient of friction, it's only 12% of the normal force. This I haven't memorized. I'm guessing it's somewhere north of 2 newtons. Okay, so force of friction is equal to mu k times Fn. So 12% of 19.62 is, 2 newtons and change. Excellent. Now we can solve for our horizontal dimension. Fh in the positive direction, subtract the force of friction. So we have 5 newtons, subtract 2.354 newtons. And that will give us a residual force of 2.6. Divide that by our mass of 2 kilograms, and we get an acceleration of 1.3 meters per second squared. So you can see how much of an impact friction has on objects. That's why if you're trying to move an object, you want to have a coefficient of friction as low as possible. Think about fidget spinners. Okay, they have these things called ball bearings, and they reduce the coefficient of friction quite significantly. Let's finish off with a two-dimensional problem, which will become one-dimensional afterwards. Okay, so if you recall from day 3.02, example number 1, there was a force that was being pushed at a diagonal. If friction was turned off and we're just to solve for the horizontal component, we find out that the corresponding acceleration would be at 1.2 meters per second squared. That's without friction. Let's say that we have this gliding on Teflon, which may seem like nothing at all, 0.4% coefficient of friction. But any form of friction is bad. Okay, so that's why I want to minimize that number as much as possible. So let's see how much 4% can do with regards to the big damage, with regards to the corresponding acceleration at the end. All right, again, in these problems over here, there's no point solving for the x dimension first. We're better off solving for the y dimension because we need the Fn in order to solve for the force of friction after the fact. So F net y is equal to Fn, subtract Fg, subtract Fh in the y dimension. F net y is going to equal to? Excellent, 0. So we can solve for our Fn now. When we bring these terms over to the left-hand side, they become positive. So Fn is equal to Fg plus Fhy. Fg is equal to mg, so 2 kilograms times 9.81. Fhy, as this is beside 30 degrees, you'll want to multiply your Fh, which is 5 newtons, by the cosine of 30 degrees. Sub all the numbers in, crunch it through, and you'll get your normal force. Next, we need to find out our force of friction, where in this case over here, it's 4% of 23.95, which may seem like nothing, but it does add up quick. Okay, seems like less than 1 Newton, not a big deal. Well, take a look at what we're fighting against. Okay, we're fighting against Fhy, which is not 5 newtons. Remember, your 5.0 newtons is your total force acting at a diagonal. Some of it's being wasted vertically. Whatever is left over is allowing you to accelerate forwards, and that so happens to be the sine of 30. And sine of 30 is always half. All right, so 5 newtons times a half, which is what's going to work out to. 5 newtons times the sine of 30, which is half, which is 2.5. 2.5 subtract 0.9. Well, now it's going to be quite significant because now the numbers have dropped to the point where that's all you're accelerating at. Okay, you're originally moving at 1.2 meters per second squared. Now you're down to half its original rate of acceleration, even though the coefficient of friction was rather low. Okay, so watch out for your frictional values. That's it. Okay, we'll take up the homework too. Why not? A sled of mass of that has 18 kilogram child on top of it. So for your free body diagram, you need to add both of these masses together. So 18 plus 26 gives you, what, 44? Yay, 44 kilograms. Big brother's pulling with a force of 30 newtons to the right and 10 newtons up. Big sister is 40 newtons to the right and 16 newtons downwards. Calculate the force of friction and the acceleration of the sled and the child. First off, we got to find out the normal force. And with the normal force, all we're dealing with is the vertical dimension. This is a fairly straightforward question. I usually won't give questions like this on any quiz, test, or exam because it's too straightforward. Instead, I'll just tell you that big brother's pulling this way and big sister's pulling at another angle, right? But this problem has it all solved into its components. So we know that Fn plus 10 newtons subtract Fg subtract 16 newtons equals, good, 0. All right, F net y is equal to 0. So you go through all the math and you solve for your Fn, and it works out that Fn needs to be at 437 newtons. Okay, it's a big number because 44 kilograms times 9.81 gives you 440-ish. All right, so you have to have a force upwards that's pretty big as well in order to compensate for it. So that's our normal force. The snow has a coefficient of friction of 0.12. So 12% of 437 is 52. Now we could deal with our x dimension. 30 plus 40 subtract 52 is 70 subtract 52, which is less than 20. It was like 19 or 18. Sure, 18. 18 newtons. All right, 18 newtons divided by your 44 kilograms gets your rate of acceleration. That's how you solve it. Two people are moving a 10 kilogram box. Person A pushes it with a force of 30 newtons downwards. Person B pushes with a force of 20 newtons upwards. If you have a terrible coefficient of friction of 36%, what is the resulting acceleration of this? Now watch out, guys. This is not a bird's eye view, okay? It's not like you're going north, south, east, west anymore. Now it's up, down, left, right. And with that being the case, you have to factor in gravity. Okay, it's not north, south, east, west anymore. It's a perspective view. So watch out for gravity, and the fact that it's on a level surface, factor in that there's a normal force as well. I should have mentioned that in question number 7. All right, number 7 is also from a perspective view. So those are the two extra forces we need to factor in, plus the fact that there's a force of friction, here's where intuition comes in. If both people are pulling towards the right, friction must be, that's right, towards the left. Now we're ready to go. And sure, I'll solve this real time. Not a big deal. We deal with our F net y dimension first, as we want it to go to 0. That's equal to Fn plus Fb times the cosine of 10 degrees. We're looking for this component over here. Oh no, we're not. We're solving for this component here, sine. Fa is moving downwards, so subtract Fa times the sine of 30 degrees. Don't forget to solve for the force of gravity as well. So therefore, Fn is equal to Fg minus Fb times sine of 10 degrees plus Fa times the sine of 30 degrees. Carefully sub all the values in, and you'll find out that your Fn is equal to 109.6 newtons. Okay, I expect you to work that out on your own. Force of friction is equal to mu k times Fn, so 0.360 times 109.6 newtons should give you close to 40 newtons. 39.47 newtons. Next, we solve for our F net x, which is equal to Fb times the cosine of 10 degrees plus Fa times the cosine of 30, subtract the force of friction. All right, and when you work through that, you'll find out that your F net, I don't have that answer. Okay, I don't have that as a cheat sheet. But whatever that is, you divide by 10 kilograms. I suppose your F net x is equal to 6.211 newtons. That only makes sense because acceleration is equal to F net minus mass. So 6.211 newtons to the right divided by 10 kilograms gives you 0.62 meters per second squared towards the right. As for number 9, a crate of 20 kilograms is being pushed by a person moving at a constant velocity. All right, what does that tell you about your F net? It's equal to 0, both in the y dimension and in the x dimension. All right, so F net y is equal to 0, so our normal force is equal to the force of gravity, where again I memorized it, 19.62, no, 196.2. Do I have that shown over here? No. Well, your Fn will be equal to 196.2 newtons. Show all your work. All right, and we need to figure out what percentage of it. Oh, we don't know it yet. Okay, we're still solving from UK, and that's fine. All right, so we're just stuck with a generic statement over here because we know the mass, we know the gravitational field strength, but we don't know this yet. We move on into the x dimension. In the x dimension, we know that F net x is equal to 0 as it's traveling at a constant velocity. So F net x goes to 0. That's equal to the force of person subtract the force of friction. So the force of the person is equal to mu k times mg. All right. We know that the person's force of 63 newtons. We know mass. We know g. We can just simply isolate from mu k and get to our answer. Goodies? Number 10, an 81 kilogram basketball player tries to slide into second base. Coefficient of kinetic friction between the player and the ground is 0.49. Now remember that when you're just sliding to your home base, you're not applying any more forward force. It's just your momentum or the inertia of your body that's allowing you to move forwards. So the only thing that's really slowing you down is the force of friction. Okay, so please don't draw any forward forces. You're trying to decelerate at the end of the day. Okay, so that's all that you have for your free body diagram. Next, we're going to try to solve for our normal force. So the normal force is calculated from our F net y. I know this seems redundant, but please always show the step. As I've mentioned many times, you're awarded for showing your work in high school physics as opposed to the final answer. So please show all these steps. Fn minus Fg. Fn is equal to mg, which is equal to 81 kilograms times 9.81 newtons per kilogram, which is equal to 795 newtons. Force of friction is equal to mu k Fn, 0.49. So roughly 50% of 795 newtons should be close enough to 400 and change. Oh, sorry, less than 400. 390 newtons. Okay. That's the magnitude of the frictional force. We're done. What is the initial velocity? Well, that becomes a kinematics problem because we need to find out the rate of deceleration. Okay, A is equal to F net divided by M, or F net is equal to negative 390 newtons, right? Because force of friction goes in the opposite direction. Divide that by 81 kilograms, and you find that the acceleration is at negative 4.81 meters per second squared. In other words, 4.81 meters per second squared towards backwards, towards backwards direction. And that helps us out in our kinematics problems, because now we have our acceleration. We have our initial velocity. Oh, sorry, we have our time. And remember, he's coming to a stop. So in other words, your VF is equal to 0 meters per second. You could figure out how long it takes for the person to come to a stop. That's not this question here. It's asking for what VI is. And looking at these guys over here, you probably want to use the kinematic equation of VF is equal to VI plus A delta T. Isolate for VI. VI is equal to VF subtract A delta T. So 0 meters per second subtract 4.81 meters per second squared times 1.6 seconds. Double negative will give you a positive answer, and that should work out to positive 7.7 meters per second. That's number 10. All right, number 11 is a challenging question. Interesting. What force is required to accelerate a lawnmower of mass 12 kilograms to 4.5 kilometers per hour from rest in 3 seconds? We'll start off with our free body diagram. The first case is without friction. Okay, so it's just applied forwards force. That's all there is. Okay, without friction present, you know that F net y is equal to 0. There's no point solving for that anymore. So we just have to deal with our F net x. And we know that F net x is equal to ma. It's also equal to the force applied. So the force applied is equal to 12 kilograms. And since we want to accelerate, oh, dear me, we got to sit down and do some kinematics. You have your VI of 0 meters per second. You have your VF of 4.5 kilometers per hour divided by 3.6. Is that 1.25? It is. And we need the third thing, which is time. Yep, we can solve for acceleration with this. We have our formula of VF is equal to VI plus A delta T. So A is equal to VF minus VI all over delta T. So 1.25 meters per second squared, subtract 0 meters per second. No, not squared, meters per second. All divided by 3.0 seconds. And oh man, 5 over 4 divided by 3. I'm too tired to figure that out. 1.25 divided by 3. 41667 meters per second squared. Okay, 0.41667 meters per second squared. I have a feeling that'll give me a clean answer afterwards. Because if I multiply that by 12, yep, 5.0 newtons. Okay, so that's the forward force applied in order for it to accelerate at this rate of acceleration. Okay, now if there's friction present, now we have to factor that into our calculations with this picture over here. Okay, so now our F net in our x dimension is equal to force applied subtract the force of friction. And we already know that our F net x is equal to ma. All right, so ma is equal to force applied subtract mu k times mg. Oh, do I have to prove that to you guys? Yeah, I guess I do. All right, let's go through this properly. Okay, our F net y is equal to Fn minus Fg. Since F net y goes to 0, Fn is equal to Fg, which is equal to mg. We also know that the force of friction is equal to mu k times Fn. So if we sub this into here, we have Ff is equal to mu k times m times g. Please show all your work. So your F net is equal to ma, and that's equal to force applied, which we're trying to solve for, minus mu k mg. So our force applied is therefore equal to ma plus mu k mg when we isolate for it. Our mass is 12 kilograms, and we determined that our acceleration needs to be the same at 0.41667 meters per second squared, plus a mu k of 0.80 times a mass of 12 kilograms times the gravitational field strength of 9.81 newtons per kilogram. 12 times 0.4 0.1667, which I already know is going to be equal to 5. All right, but here's the thing. Friction makes your life worse. All right, so you know that you need that first initial 5 newtons to accelerate it at the rate that you desire it to be, but you also have to fight over the force of friction as well, and that's why you'll see mathematically you're adding the force of friction on top of it. Okay, so plus 0.8 times 12 times 9.81, and that's why our number is going to be much greater. That force of friction is an evil one. Okay, 99 newtons now in order to drag it forwards. That's why we want to have ball bearings. Thank you, fidget spinner. All right, number 12, a curling stone. Free body diagram for me? Good, it's decelerating. So we probably want to do kinematics first, don't we? Let's do that. Do I have that written down over here? Yay, kinematics first. Because we have our VI, we have our VF, and our delta D. Okay, so we are going to be using the formula VF squared is equal to VI squared plus 2A delta D. A is equal to VF squared minus VI squared all over 2 delta D. VF of 0 meters per second squared minus 0.885 meters per second squared divided by 2, 31.5 meters, and it's decelerating, so we should expect a negative answer. So 0.885 squared divided by 2 divided by 31.5. So I'm getting lazy now. It should be a negative answer. So negative 0.01243 meters per second squared. All right, that's our rate of deceleration. And we're trying to find the coefficient of friction now. Sweet. So once again, F net y will go to 0, which is equal to Fn minus Fg. In this case over here, Fn is equal to mg. Force of friction is equal to mu k Fn. Sub that in, and the force of friction is equal to mu k mg. Yes, show all work. Okay, please do not just say FF is equal to mu k mg. You've lost 2 marks by not showing your work. Show me how you got to it. Okay, and if you have the values, then by all means sub it in. No, we don't know the coefficient of friction, so we'll just leave this alone. Equation number 1. Next, your F net x. Well, F net x is equal to ma, and that's equal to negative force of friction. So ma is equal to negative mu k mg. And this really reveals something really interesting. You'll see that m's are on both sides. So really, it doesn't matter if the mass was 20 kilograms or 200 kilograms. Your coefficient of friction would be exactly the same. Mass didn't matter. Okay, so therefore, if we isolate for our mu k will be equal to negative a over g. Is that all we got? I think so, yeah. So our rate of deceleration of negative 0.01243 meters per second squared divided by 9.81 newtons per kilogram will give us a very small coefficient of friction. Nice. Nice, ice. 1-3. And we're good to go. Now you know. All right. I've also asked for you guys to work on how many more questions? Oh, boys. Okay, last one. Last one. Sorry about this. Okay, this is a very messy diagram, and the first thing you want to do is you want to figure out which side is winning. Is it winning towards the left, or is it going to win towards the right? All right, so you'll just do some very quick mental math over here. So on the right-hand side over here, we have, oh, actually, this is terrible because this is not a free body diagram. You got to convert it into a free body diagram. Okay, so these forces over here, they're still correct because they're pointing in the correct direction. But as for this guy over here, that should point away from the box. This guy should point away from the box as well. So that's a proper diagram over here. Next thing we're going to do is we're going to see who's the winner. On the right, we find out that FD plus FA times the cosine of 20 gives you a 68.5. On the left, FC plus FB times the cosine of 40 gives you 25.3. And you can see winner, winner, chicken dinner, it's moving towards the right. And if moving towards the right is the winner, now you know which way the force of friction will be, which will be towards the left. All right, so that's the first exercise you got to sit down and figure out. And after you're done with that, now you can get the party started. F net in the y dimension goes to 0, which is equal to the normal force, which is positive, subtract 3 downward forces. FB times the sine of 40 degrees minus FG, or if I want to replace it with MG, that's perfectly fine, minus FA times the sine of 20 degrees. So the normal force is equal to, I'll just drop right in right now, FB, which is 20 newtons, times the sine of 40 degrees, plus 10 kilograms, plus FA, which is 25 newtons, times the sine of 20 degrees. I forgot to write down 9.81. Good thing I've done my homework so many times, I know what to do next. So make sure you do your homework every single night, and you'll get your answer. That seems about right. 119.5 newtons. 51 newtons. Sure. There you go. Your force of friction is equal to mu k times Fn. In this case over here, your mu k is just 20% of 119.51 newtons. Oh, I had that already calculated out. Huh. Oh, all right, so I didn't have to do that part over there. That's given to you right over there. So our last part, and I'll just write it out for you. F net in our x dimension. If you want to go and cut to the chase and say it's equal to MA, I'm fine with that. MA is equal to your FD plus FA times cosine of 20 degrees. Subtract 3 backward forces. FC, FF, and FB times the cosine of 40 degrees. Since I already have it animated out, oh, it's not, so yeah, I'll just show this to you. Okay, FD is equal to 45 newtons plus 45, oops, sorry, FD, yeah, 45 newtons plus FA, which is 25 newtons, times the cosine of 20 degrees, minus FC, which is 10 newtons, minus our force of friction of 23.90 newtons, subtract FB, which is equal to 20 newtons times the cosine of 40 degrees. $19.27. And the mass is 10 kilograms. So 10 kilograms times A is equal to 19.27. Therefore, A is equal to 1.93 meters per second squared towards the right. And we're good to go. That's it. Catch you guys later.